This is the cover page to the exam. You have homework for me?
Oh.
Can I borrow it for 2 seconds?
Carry that.
Thank you. Hey, I gave it to me forever. Thank you. I need to get one of those.
The important part is the one down here at the bottom. You are permitted to use by 1 8.5 inch by 11 inch handwritten formula sheet. The sheet must be turned in with your exams, may only contain formulas, definitions, rules, and such on one side. There may be no worked out examples. Your name should be on the other side. Be penalized for inappropriate items on your formula sheet. So write what you want, but I'm going to look through it carefully.
We're not gonna work out examples of anything. Okay.
So just like, what was the tables?
The tables are absolutely, those are not worked out examples, right? That's just a general rule. Those are perfectly acceptable, but don't work out a particular example separately. And if you've got questions about it, come ask me. I'll happily talk to you about them. Meanwhile, I want to take a slightly different tack and examine the idea of sets and set theory. Just as all of what we have been doing for the entire month so far has been based off of the idea of formal propositional logic, all of this can equally be defined and described in terms of sets. The formalization of formal logic goes to people like Peano and Zermelo and Frankel. The formalization of set theory goes to Russell and Whitehead. And between these groups of people, they came up with ways to cross the streams so that we really have two different perspectives on the same idea. But I need to start with the basics. What's a set? I'm going to go a different way. I'm going to say a group of things, right? Unique is a separate idea. Let's just go with a group of things. An unordered collection of objects. Now, I'm being particular about unordered here because that is a very wrong button. A very specific piece of what we're going to look at. So I could describe a set like set of books in my office. Here's where my uniqueness issue comes into play. I happen to have 3 copies of this textbook. Are they unique? Are they distinguishable from one another? I could lay them out and then pick which one I was looking at, but they're really all effectively the same, aren't they? You are a set. The set of students in SMA205, spring 2025. Set of even integers. The set of Dr. Sassmore's daughters. The term object here is deliberately left unspecified. We can have sets of any pile of objects. There are some unfortunate consequences to this. And some of these paradoxes that resolve weren't actually worked out and made clear until less than 100 years ago. So some of this is going to cause problems. An example of such a paradox. Is this a set? I mean, you pick up a book, this textbook, and if I open it to this page, it says, hey, go back to page 37 and notice that, or as we saw in chapter 2, this book does refer to itself. But if I pick up my copy of Harry Potter and the Sorcerer's Stone, it doesn't say in chapter 16, hey, go back and look at chapter 5 and remember that we saw. It doesn't say, oh, turn back to page 32. Never does that, right? That book would be on this list. Most fiction books would be on this list. It is rare for a fiction book to refer back to itself. This is a large collection of objects, isn't it? I'm gonna restrict myself a little. And I will include the library, professors' offices, dorm rooms, other lounge libraries, whatever, everywhere on campus. I got a lot of books for this list, don't I? So I go and I make a physical copy of this list of books. It's a lot of books. I'll take this paper and I'll bind it. I just made a book. It's here at Seton Hill. We'll call it non-self-referential books. Does it refer to itself? Then it should be on the list. But if it's on the list, then this book refers to itself, and it can't be on the list. The list is books that don't refer to themselves. Houston, we have a problem. This should be on the list, but if it is on the list, it shouldn't be on the list. But if it's not on the list, it should be on the list. Mother, what do I do? I don't. Just like we decided that certain sentences were not actually propositions. This thing is not a set. Because we cannot clearly decide what things are in it and what things aren't. If that definition is fuzzy or unclear, then the object in question is not a set. So in spite of the fact that it made perfect sense for me to talk about this collection of books, I'm going to be a pain in the ass and say, yes, it's a collection. No, it's not a set. Questions?
If you had a collection of books that do refer to themselves, that refer to themselves.
Okay, so like our textbook.
Yeah.
Then I print out that list. The book of books that refer to themselves does not currently refer to itself. I don't have to put it on the list. If I do put it on the list, then it refers to itself and it belongs on the list. That's what works.
So as long as it's not a contradiction.
A paradox.
Paradox.
Something that should be true and false at the same time is not a valid proposition. Something that is in my set and not in my set at the same time makes that thing not a set. Some sets are perfectly clear. The set of Dr. Sassmore's daughters. I have one child and he is not my daughter. That set is empty, contains no members. Members or elements. And a set contains all of those members or all of those elements. So the things in a set are the elements of that set. They are contained in the set. I use descriptions up there. But a lot of times we actually list out the elements of a set inside a set of curly braces. Here is a set containing the numbers 1 and 3 and 5. I'm going to name the following set V. These are letters in the English language that are always used as vowels. An explicit listing like this does not prevent me from having elements in a set that have nothing in common. This is just a pile of random stuff I found and put in a box. That's a set. I can tell you exactly which things are in it, which aren't. If there is a clear pattern to the items I am using, then I can, instead of just listing every one of them, I could list out and then say, hey, the pattern continues. That ellipsis, that set of 3 dots right there, should indicate a clear pattern. What have I listed in this set?
Increments of 1 all the way from 1 to 100.
Positive integers from 1 to 100. There we go. Perfect. And then I can look at any given number and say, is it in the set or is it not in the set? 73 is in it. 246 is not. Pi, that's not even an integer. It's definitely not in there. Frequently, because I'm a math person, I will use sets of numbers. And most of those sets of numbers are given these funky looking letter symbols with that doubled line somewhere in them. And that's usually to indicate what was usually written on a blackboard with the wide side of a piece of chalk. So that font is called blackboard bold. That extra Z would be written with the side of the chalk. The Q would have part of this Q circle drawn wide. Well, okay. Natural numbers, integers, rational numbers, real numbers, complex numbers, different sets of numbers get used in different purposes. An interesting point. A difference between American English and British English. You walk off the street into a building. What floor are you on? Aha! If you're in England, you're on the 0th floor, the ground. If you're in America, you're on the 1st floor. So when I start talking about the natural numbers, where does it start? With 1 or with 0? That depends. And this is what's going to piss me off. Different books use different definitions. Until I got to this textbook, to me, the natural numbers started with 1. This textbook, the natural numbers start with 0. But you're going to have to be on the lookout. If you go online and look at something else, and they talk about the natural numbers, do they include 0 or not? It's going to depend on your source. 99% of the time, I'm going to remember to use 0, but every now and then I will forget, so somebody call me on it when I make a mistake. All of these sets of numbers have an order to them. We know which number is bigger and which number is smaller. The complex numbers are two-dimensional. Complex numbers are numbers of the form a plus bi, where I is the square root of -1. Well, you can't take the square root of negative. Yeah, I know. I made something up. We're going to call it this I, and it still works. People like Vessel and Argand and Lambert gave us this idea and made it work. And originally it wasn't called an imaginary number, it was called a lateral number, because you thought of it as kind of sideways to the rest of the numbers. You squared something that was negative. I promise there's a really pretty geometry picture there. Anybody who's interested in complex numbers, stay at class, it'll be really cool. But it's a separate issue. These don't have an order to them. I don't know which ones are bigger and which ones are smaller. But it makes sense for me to restrict these numbers. Natural numbers are all positive. Integers are positive and negative, right? So I could talk about something like the positive integers or the negative integers. Same thing with real numbers or fractions. Sometimes we just want to take away 0. And if we just want to take away 0, we use a little asterisk. In that case, I can do the complex numbers. All the complex numbers except 0. That works. So positives only, negatives only, non-zero only. But since these have 2 parts to them, telling me which one is negative, which one is positive, what if one's each? It doesn't make sense. The same way it does over here. Questions? Yes, sir.
What is the same parentheses?
Solid, which is why it's a Z, because that's the word in the paper that described this as a set the first time. Zahlen, I believe, is German for integer. You'll see in a number of engineering textbooks, sometimes instead of Z, you'll see J. And again, I want to bold that downward piece of the J. I don't know where the J came from. But a lot of the engineering books use J instead of I. I'm going to use Z all the time for my integers. More questions? Two sets are equal if they contain the same elements. Makes sense, yes? There's just one problem when I write this. Remember we had a set earlier that had 3 positive integers in it? That set? Is that any different? No. There's the 5, there's the 1, there's the 3. Remember in my definition, I said an unordered collection of objects. Is that different? No. Where's this one up here? Right there. Where's this one? Right there. Where's this 3? Right there. Where's this 3? It's also right. Now you see why I didn't say distinct objects when you gave me that in the definition set. There's nothing in here about distinct. I hate the fact that all 3 of these sets are considered equal, but they do contain the same elements. The third one has more of them, but I'm not counting repetition at this point. I'm just counting membership. There's a 3 in both sets. There's a 1 in both sets. There's a 5 in both sets, and there's nothing else. They're equal. I don't like it, but it works. Question. We will add the idea of distinct to our sets later on, but at the moment we're not. Another way to describe a set, instead of just listing stuff out, is to describe a property they satisfy. That's a logical sentence. Take all the things where this property holds. Now, I wrote it out in words, but what we've got here is a set we've already seen. These are the numbers 1, 2, 3, 4, ... 99, 100. We wrote it out explicitly. But here it is. Find all the x's, then there's that vertical line. I'm going to read that vertical line so that. Or such that this property is true. Which means if I wanted to be a geekier person and write it out in math symbols, I could. But there's no requirement. I just have to be able to decide. Oh, wait a minute, I missed something. I didn't specify integer. This is wrong. That funky looking E, X is an element of. Or is a member of, or belongs to the set. I often read it as in. X is in the. Now, I could also take that X in Z part and put it on the left of the line. So another way to write this same thing is to write that. Take the X's from the integers, make them satisfy this problem. This is referred to as set builder notation. X in a set such that P of X is true. And then P of X has to be a propositional function. And I will return true or false as a Boolean. Take all the places where it's true. Hey, wait a minute. That means the set of elements that satisfy a proposition is its truth set. We were in the universe of horses, or the universe of dogs, right? Dogs have fleas, right? Okay, find the dogs that have the fleas. There you go. We have the truth set of this proposition. I think we had to negate that proposition on a homework problem, something like that. This allows me to describe the set of my daughters. What did we say was the set of my daughters? A set with no members. Not the same as zero. A set with no members is called an empty set or a null set. And it's indicated by a pair of braces with nothing between them. Oh, there's nothing in my set. Or the lowercase Greek letter phi. This usually pisses off computer science people who get told to write that for zero instead of, so they can tell zeros and O's apart. To math people, that means something very different. If you don't like thinking of it as an O with a slash through it, think of it as a Norwegian letter. Then it really looks like a big circle slashed. It looks much better in that font. However, I can think of this as an empty box, right? A null set. If this were also empty, this would be a null set, yes? What's that? Not a null set anymore. So the thing you cannot write, don't write this. That's a box holding an empty box with a box in it. It's not empty anymore, is it? That set has one thing in it. What's the thing inside it? An empty box. My box is off of Amazon. That's how they send them to me, right? Boxes in boxes. Question. Okay. I think of sets as I did with propositions, as universes of discourse. Here's the pile of stuff I'm talking about. Whatever that pile is. So if I'm going to make a diagram of a set, I'm going to consider the universe I'm working in as some big container, my box. And then I'll label a set inside it. Here's my set A. I know. The set of English letters that are always used as vowels. We call that set V. So I'll name it V. And it contains A, E, I, O, U. And then out here are all the other letters. But I have to specify my domain, just like I did a domain of discourse, a domain of definition in my propositions. This is a Venn diagram. A lot of Venn diagrams have multiple sets in the same universe. We'll talk about those more next. But for the moment, I'm just thinking of a universe and then a set within it. Questions? The advantage of windy days, the room howls. If I have two sets that live in the same universe, then I can use this symbol, which isn't quite less than or equal to, that's a rounded top there, for containment. A is a subset of B. Well, what does that mean?
A or B, but not all of them. B or
It could be that they are actually equal, right? This is contained in or equal. See, that's that extra piece. That's the equals part. If I want to try again. If I want to speak strictly, then I should write that. See the difference? But really what that means is that I can do my subset. Hey, wait a minute. I see logical connectors again. A is a subset of B if for all X in A, that implies X is in B. Or if you'd rather, for all X, if X is in A, then X is in B. There, it reads more like an if-then sentence if I write it that way. If there's something in B that isn't in A, then I'm in this position. But otherwise, they could all be there. Here's a claim. Okay, remember when I was talking about methods of proof? And I talked about vacuous and trivial proofs, and I said they were really weird, you rarely saw them. I got one of each right here in front of you. I'm going to prove that first sentence. What do I need to show? I need to show this idea. For every X, when X is in the first thing, then X is in the second thing. So pick an X in the empty set. False. False arrow anything is always true. It's a vacuous proof. On the other hand, This one. Pick an X that's in S. Is it in S? Didn't you even tell me it was an X? Therefore, it must be an X. I'm done. This is a trivial. The consequent is already true. Pick an X and S. It must be an S. This is a trivial proof. It turns out, rather than actually saying two sets are equal if they contain the same things, it's often easier to show that two sets are equal if they are subsets of each other, like an if and only if proof. Think about it as if they were numbers. The only way A is less than or equal to B and B is less than or equal to A is if A and B are equal. Showing containment, showing subset behavior is almost always easier than going through and listing everything in a set to show that they are the same. Questions? They promised me window shades at some point, which will cut out the noise, but they weren't in the first round of budget to do all the tech in his room, so that's later. Sets can be parts of other sets. Let us consider a set whose elements are sets themselves. I took the set AB, the set of two things, and I looked at all the possible subsets it could have. I could take nothing. That would be the empty set. I could just take the first thing, A. That would be the set containing just A. I could take the set containing just B, or I could take the whole thing. These are sets as elements of another set. Given a set, S, the set of all subsets of S is called the power set of S. What we have written up there, the empty set A, B, AB, that's a power set. This is the power set of a set with two elements. We do this often to count things. We count subsets, which means I want to talk about counting in a set. If I want to count things, I need to be able to tell them apart. The cardinality of a set, S, usually written as the absolute value of S. Sometimes it's written as N of S. Sometimes it's written as number of S. That's not a hashtag. But I'll use this absolute value idea. Is the non-negative integer n so that there are exactly n distinct elements in S. Here's where I get Seth to add back in different. And what that means is that officially this set contains three things. Twitch, 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 twitch. It contains three distinct things. Please notice cardinality is finite. Got to be an integer. If no such integer exists, then S is an infinite set. So, the natural numbers, that's infinite. The fractions, that's infinite. The real numbers, they're also infinite. The complex numbers, they're also infinite. So we have a lot of infinite sets. We have a lot of finite sets. We laid out the integers from 1 to 100. That's got 100 things in it. We laid out a set that had 3 numbers in it, 1, 3, 5. I promise I have more to say about the idea of infinity, because infinity has flavors. There isn't just one infinity. Questions? Yes, sir.
Can you repeat briefly your explanation from the cardinality to the end of that?
From here to here?
Yes.
Okay, so I'm counting the number of things in my set. If it's finite, 1, 2, 3, 4, 5, 6, 17, or 17 things in the set. Great. I want to count the integers. 0, 1, -1, 2, -2, 3, -3, 4. Am I ever going to stop? There's no integer that ends the set. That set is infinite. And all of these sets are examples of infinite. But I promise there's more to come on that. Infinity is weird, man. An interesting question for you. We did the power set here earlier, right? And I said the power set was about counting. There were 2 things in here. The power set had how many things in it? Okay. If I gave you a different set, let's say the set ABC, what would be the cardinality of the power set? 4 things, 5 things, 6 things. What happened? My power set is bigger than the original set. Anybody here play brass? Trumpet, tuba, French horn? Have you ever seen anybody play a trumpet? How many valves on a trumpet? Either 3 or 4. Upright sousaphone usually has 3, sometimes has 4. Depends on that, right? Well, how many different valve combinations are there? Well, you pick which ones to put down. You pick a subset, right? You can put them all down. You put none of them down. Put one down. That's a power set. The fingering positions on a trumpet are exactly a power set. Same thing on a saxophone. Only there are a lot more options, right? And some keys push down multiple things at the same time. A recorder with all the different holes, same idea. How many different ways you can create that structure is a power set. We use it all the damn time, we just don't think about it. Yes, ma'am.
So with the set of the 111, 333, 55
Mhm.
being just 3 numbers, or just
3 distinct numbers.
could you put 2 sets together to count them?
Sure.
So like if you had 3 1, 3 2, 3 3, and then you could count the stuff.
I could make an ordered pair. And the ordered pair could tell me what element and then how many times it shows up, right? And now I've got a new set that I made from the list of the numbers 1, 3, 5, and the set how many times each one shows up. But that's not actually this. This Cartesian product allows me to look at every possible ordered pair that I can make. So if I had the numbers 1, 3, 5 for my set A, and the colors red, blue, and yellow for the set B, how many things would be in the Cartesian product? So I really want to think about my Cartesian product, and then I want to think about some way of identifying subsets within that Cartesian product. We'll talk about that more in chapter 2, section 4. Please notice, if you reverse the order, if you do B cross A rather than A cross B times, if you do it in the other order, you get a different set. Because the only way 2 ordered pairs are the same is if the first things are the same and the second things are the same. By the way, if you can do it for 2 sets, you do it for 3 or 4 or 5 or however many you want. Cryptography and cryptanalysis deeply depends on my ability to look at Cartesian products. Geometry. I can think of R cross R. Algebra. I don't even need to do geometry. R cross R consists of ordered pairs, right? Number in the first, common number in the second. If I label them X and Y, isn't that exactly this thing? The Cartesian plane, the Cartesian product. Rene Descartes, same dude, same idea. The thing you're looking for, Emily, is called a relation. A relation from the set A to the set B is some particular subset of the Cartesian product. So if I had 1 red, 2 green, 3 yellow, that would be a relation. Relations are special types of functions. But in order to define functions, I need to continue with my ideas of how the logical works on here. So I need to do and, or, not, all of these other things in set terms. That is what we will do on Wednesday. So I will see you all then. If you came in late and have not given me your homework, please come give it to me. I will see you all on Wednesday.